Okay, students, it's still a gas, gas, gas. In the first lesson, we learned about the ideal gas equation, PV equals nRT. We learned that 1 mole of most gases under what we will later call standard conditions of 1 atmosphere pressure, 1 mole, and 273 Kelvin occupies approximately 22.4 liters. Okay, that was the first lesson. In this lesson, we're going to take up a few other relationships involving that equation, PV equals nRT. One of these is the relationship between the density of a gas and its molecular weight. Now, if you think back to that last table we had where we had 3 different gases, I think they were hydrogen gas, oxygen gas, and carbon dioxide gas, and we said they all occupy about 22.4 liters under these standard conditions, 273 Kelvin, 1 atmosphere pressure. Yet, the mass of the gases, the mass of 1 mole of these gases would be different. 2 for hydrogen gas, 32 for oxygen gas, 44 for carbon dioxide. So they would occupy about the same volume, but they would have different masses. So that will tell you that a container of gas will have a different density depending upon the identity of the gas. The relationship is shown in this slide. The molecular weight of the gas, which of course is related to its identity, the molecular weight of a gas is equal to the density of the gas times this gas constant, R, times temperature divided by pressure. You will see that you can rearrange this equation to another form that will be handy, solving for density. Density is equal to molecular weight times the pressure divided by the quantity R times temperature. Let's give you a few examples. Let's calculate the density of hydrogen gas and carbon dioxide gas at these standard conditions of 273 Kelvin and 1 atmosphere pressure. For hydrogen gas, a molecular weight of 2 grams per mole, 1 atmosphere pressure divided by the gas constant R, 0.082, and times temperature, 273, we would calculate the density of hydrogen gas to be 0.0893 grams per liter. Now note that we usually express the density of gases as grams per liter, whereas for condensed phases of matter, solids and liquids, we generally express their density as grams per milliliter or grams per centimeter cubed. Okay, but because the density of gases would be much smaller number if expressed in that manner, we express their density instead in grams per liter. So we've calculated the density of hydrogen gas. It's a small number, 0.0893 grams per liter. If you do the same calculation for carbon dioxide, you get 1.965 grams per liter. Now, this type of application of this equation may not be as interesting, but another one is a little bit more. We can use this equation, molecular weight equals density times R times T divided by P, to calculate the molecular weight of an unknown gas if we can determine the density of that gas, if we can experimentally determine that density, which we can. We can oftentimes determine the mass of a sample of the gas and the volume of that gas to get the density. So if we can experimentally determine the density of gas, we can just multiply by R in temperature and divide by the pressure under which we're doing these experiments and determine the molecular weight. And that will, in most cases, allow us to identify the gas from its molecular weight. Another application of the ideal gas law involves partial pressures. This really relates to mixtures of gases, when we have 2 or more gases in the same container. For example, air, the air around us, is a mixture of gases. It contains about 80% nitrogen, maybe it's 78%, but about 80% nitrogen, and about 20% oxygen, and then a percentage or so of a few other minor gases, argon and carbon dioxide, water vapor. But for all practical purposes, we could consider air to be 80% nitrogen, 20% oxygen. So keep that in mind, and let's work through these equations. If we have a mixture of gases, such as air, the total pressure is equal to the partial pressure contribution of each of the component gases, the partial pressure of each of the components. So we could say, for example, if there are 2 components, A and B, 2 gas components in a mixture, that the total pressure, PT, T for total, is equal to the sum of PA plus PB. Okay, nothing complicated so far. And for each of the component gases, such as the pressure of gas A, that can be described by the ideal gas equation. So we can say that the pressure of A is equal to R times T times the number of moles of A divided by volume. Well, if you have a mixture of gases in the same container, they're in the same volume, so volume is the same, and they're going to be at the same temperature, and R is just a constant. So you can say then that the total pressure is equal to the number of moles of component A times RT divided by V. And you can factor out the RT divided by V and come up with the general relationship as shown. The total pressure is equal to RT divided by V times the sum of the number of moles of each component gas. Okay? Now from this, we can then talk about the mole fraction of component A. Mole fractions we generally express as capital X, A, and they will be a fraction between 0 and 1. So if we have a mixture of two gases, A and B, and we want to know what is the mole fraction of component A, XA, that would be the partial pressure of component A divided by the total pressure. And the total pressure, of course, is the pressure of A plus the pressure of B. So those relationships are shown to the left. Okay, and further, we can say that the pressure of A is equal to the mole fraction of A times the total pressure. That's just a rearrangement of this equation. Now, this seems like I'm throwing a lot of equations at you, but if you go back and think about air, what is the mole fraction of nitrogen in air? We said it's 80% nitrogen. That means the mole fraction is 0.8. 0.8 times the total atmospheric pressure would then be the partial pressure of nitrogen. I'll say 0.8 times 1 atmosphere. Oh, that means in air, the partial pressure that is nitrogen is 0.8 atmospheres. Okay, and likewise for oxygen, we say 20% oxygen, or the mole fraction is 0.20 for oxygen. 0.20 as a mole fraction times the total pressure of 1 atmosphere. That means that in air, the partial pressure due to oxygen is 0.20 atmospheres approximately. So that's how we use these relationships. Now for a mixture that contains only two gases, these equations are easy to handle. Just try them and always keep in mind the example of nitrogen and oxygen in air and work through, and you'll not have any problem understanding partial pressures. Again, when we're talking about mixtures of gases, there will be a part of the pressure, part of the total pressure that is associated with each of the component gases. That's all you need to remember. And the equations work because in a mixture of gases, the gases act independently of each other, and each gas obeys the ideal gas equation. Okay, as promised, we will now talk about some stoichiometric problems with gases as either reactants or products. Okay, let's consider starting with something like silver oxide, Ag2O. And let's say we start with 2.32 grams of silver oxide, and we heat it up to undergo this reaction where the silver oxide decomposes into silver metal plus oxygen gas. And the question will be, what volume of oxygen gas is formed at, say, 273 Kelvin in 1 atmosphere when we start with this amount of silver oxide? Let's see, how would we do this problem? Recalling our stoichiometric problem-solving skills, we set it up in the following way. We start with the mass of the reactant silver oxide. Okay, the first thing we always do is we convert it to moles by dividing by the molecular weight of 232 grams per mole. Oh, nice numbers. So that we determine that we started with 0.01 moles of silver oxide. All right, so if we started with 0.01 moles of silver oxide, how many moles of oxygen gas would we form? That's right, we look at that stoichiometric relationship. One oxygen molecule formed for every 2 silver oxides that we start with. So we take the 0.01 moles of oxygen multiplied by 1/2 to get 0.005 moles of oxygen gas would be formed. Right, so that's our N. Now, what do we do next? Well, what was the question? The question was what volume of oxygen gas would be formed in this reaction? Well, let's see, that's the number of moles, 0.005 moles. We're given temperature, we're given pressure. Oh, we just insert this into the ideal gas equation. PV equals nRT, but if we solve for volume, that equation becomes volume is equal to N, moles, times R, gas constant, times temperature, 273, divided by the pressure, 1 atmosphere. So we just insert these values, and we determine that the volume of oxygen gas that would be formed would be 0.112 liters. See, it's not so bad. Now, this problem can also be solved in reverse. So we can be asked, for example, what mass of silver oxide is needed to produce 4.58 liters of oxygen gas as a product. Let's say for some reason we want to produce that many liters of oxygen gas. At what temperature and what pressure, you ask? Well, in this problem, what if they say at a pressure of 745 millimeters of mercury and at a temperature of 308 degrees Kelvin? Oh, that means it's not 273, but it's 308. I can still handle that. But the pressure is 745 millimeters of mercury. That means I'm going to have to convert that to atmospheres. And how would I do that? By dividing by 760 millimeters of mercury, because there's 760 milliliters of mercury per 1 atmosphere. Okay, so to solve this, first of all, let's convert our pressure to atmospheres by dividing by 760. The temperature is already in Kelvin. Okay, so we've got those under control. To solve the problem in this reverse direction, we take the information we're given, the pressure, the temperature, and the volume that we want to obtain, and we solve for the number of moles in. Just plug that into PV equals nRT, or solving for N. PV divided by RT is equal to the number of moles of N. So we solve for N, and we would determine a value of N, the number of moles of oxygen that corresponds to that particular volume and pressure and temperature of oxygen gas. We would determine that the number of moles of oxygen is 0.182 moles. Now, once we have that number of moles of oxygen, how many moles of silver oxide would we need to have started with? That's right, twice that many. And once we had that number of moles of silver oxide, we multiply by the molar mass of silver oxide, and we get the mass that we have to start with in order to produce that volume of oxygen gas at that temperature and that pressure. And as I say, this is just chocolate cake. Now, there will be other gas stoichiometric problems that you'll see in the textbook. And in some cases, they'll talk about collecting gas by bubbling the product of a reaction, such as the one we just had, which was oxygen gas, bubbling that oxygen through water in order to collect the gas. This is referred to as collecting the gas over water. Now, if you're given a problem of this sort, it's just a little bit more complicated, so you need to be aware of whether or not the problem says collecting a gas over water. That is because the gas space in such an apparatus will contain not only the gas of the product, the desired gas, but also will contain water vapor. Okay, collecting a gas over water. Water itself will be in equilibrium between the liquid and the gas phase. And so you'll have to subtract out the partial pressure, see, mixture of gases, partial pressure. You'll have to subtract out the partial pressure of water vapor to get the pressure due just to the gas that you're collecting. There will be a problem in a textbook of this sort, and you should take a look at it. It's slightly more complicated, but really it's tractable. It's something you can handle. We'll pause now, and in the next video lecture, we'll begin talking about what is called the kinetic theory of gases. See you shortly.